Hi everyone, I am Gabriel Intriago. I am presenting the article Online Dictionary Learning-Based Fault and Cyber Attack Detection for Power Systems. This is a joint work with Professor Zhang. We are both at the University of California in Santa Cruz. So starting off with the introduction and going first to the problem statement. So given a set of unlabeled and labeled data, we have to incrementally build a classifier for power systems fault and cyber attack detection. Our algorithm works in the online paradigm. The reason for that is that existing monitoring devices produce data at rates of 120 samples per second or 240 samples per second. So explaining this paradigm into three steps. So in the first step, our algorithm receives the next available training example with its features and its label. In the second step, the algorithm updates its model by processing this example at most once, and it does it with a limited amount of memory and in a short amount of time. And finally, in the third step, the algorithm has to be able to predict the next unseen or test examples label. So our proposed approach has as an input a hybrid data set, which is made of data from physical and cyber measurements with unlabeled and labeled data points. So the physical measurements come from phaser measurement units and the cyber measurements come from networking devices. Our method is to learn a dictionary by extracting high-level features, which can be understood as oscillations, stable periods, abrupt changes, gradual changes in the voltages in the currents, and using these high-level features, we represent later the labeled data. So the output is a trained classifier. Our motivation is twofold. So first, power system operators and utilities, they need to learn the causality of various events, either natural disturbances, electrical faults, or cyber attacks, and they have to deal with them timely and properly. Second, previous works rely only on label data to train a classifier that discriminates events in power systems. However, it's challenging to collect real-time label data. So our work takes one step forward in these matters and uses unlabeled data to enhance the training of a classifier, considering that unlabeled data does not account for the labeling process. Moving on the methodology, we can divide it into three stages. So in the first, we learn a dictionary in an online fashion by solving optimization problem number 1. The optimization variables are the matrix D and the vector alpha sub u. Typically, the matrix D has more columns than rows to make the dictionary rich enough. So each unlabeled data point x sub u is approximately represented as a linear combination of the columns of matrix D with coefficients given by the entries of the vector alpha u. So in the first constraint, we use a zero norm to say that at most k elements are non-zero in the vector alpha sub u. And in the second constraint, we set an upper bound on the energy of the columns of matrix D to avoid that the entries of matrix D are very low and the entries of vector alpha sub u are very high. So we leverage on the alternating minimization algorithm. We do this by iteratively solving two steps. So in step number 1, we do a sparse coding. In other words, we minimize over the vector alpha sub u using the orthogonal matching pursuit algorithm. And in step number 2, we update the dictionary by minimizing over the matrix D, and we use the block coordinate descent algorithm. In the second stage, we do a new feature representation by solving optimization problem number 4, where the optimization variable is the vector alpha sub L, and we represent each labeled data point as a linear combination of the columns of the learned dictionary D star with coefficients given by the entries of the vector alpha sub L. In the first constraint, we said that at most k entries of the vector alpha sub L are non-zero. So this vector alpha sub L is in a higher dimensional space than the original vector labeled data vector x sub L. So we do this and complement it with the sparsity of the vector alpha sub L to make it easier for the classifier to partition the feature space and therefore do a better classification. In other words, we transform the label dataset by replacing the original feature vector x sub L with the vector alpha sub L, and we preserve the original labels. In the third stage, we train the classifier where we use as a base learner the Hofding adaptive tree, with two change detectors, the drift detection method and the adaptive windowing. We use the software Massive Online Analysis (MOA) for our implementations. In the experiments and results, let's first discuss the dataset. So our dataset considers 37 types of faults and cyber attacks, and we assign a label to each of these types. Therefore, we can build a 37 class dataset. Or we can group the labels into a group of two, say operation and cyber attacks, and then we have a 2-class dataset. Or we can group the labels into a group of three, say natural event, electrical fault, or cyber attack, and then we have a 3-class dataset. So our dataset has 128 attributes and around 75,000 instances among the unlabeled and labeled data points. Regarding the parameters, we set the sparsity value k equals to 10. We set the number of dictionaries columns to 130. And these parameters and other relevant parameters were set using cross-validation. On the right, we start discussing our simulations. So in this figure, we have the tenfold average accuracy and time comparison between the state-of-the-art classifier, the HAD, and our proposed approach, the SSHAD, which stands for Semi-Supervised HAD, using the 37-class dataset, where the x-axis represents the sampling ratio used to draw instances from the labeled dataset. So the blue bars are with our method, and the orange bars are with the state-of-the-art classifier. So we can see that our algorithm outperforms the state-of-the-art classifier. In the next figure, we have the tenfold average accuracy and time comparison between our approach and the state-of-the-art classifier. The solid bars are with a 2-class dataset, and the dotted bars are with a 3-class dataset. So we can see that the two approaches, the two methods, has the similar performance, but still our method is still better than the state-of-the-art classifier. On the right, we have a simulation for testing if our method was robust against bad data, and it is robust given that its accuracy values shown in this figure are with the same level when there was no bad data. And finally, their conclusions, we leverage the online dictionary learning techniques to build a new feature space for the labeled data examples by extracting valuable information from the labeled dataset. Our results demonstrate that our proposed approach is effective, it yields a better classification, and it compensates for the additional computational burden of learning the high-level feature representations. And this work can be extended by studying how a malicious adversary can modify the data, and also a more detailed analysis of the temporal dependence of the data should be considered. So thank you. This is the end of the presentation.